In this clip, I show a demonstration where they have current going through a wire, and it's inside a magnetic field, and it makes the wire jump. If you think about it, right, if you have current going through a wire and you have a magnetic field, you're going to have a force on it, just like you had with when you had one charge, right? You just have a bunch of charge now passing through. So the way that we do this, it's another right-hand rule, but very similar idea here. We have the force, and then current. This is the flow as positive charge, so we're going to use conventional current, and then B is the magnetic field, so FIB, and you can think of it as a fib, FIB. It's a fib, but it's true. Okay, FIB, force, current, field. And the way that we calculate this is multiplying the current times the length of the wire exposed to the field times the strength of the field. Current in amps, L is the length in meters, B is the magnetic field in Tesla, and the theta is the angle between the current and the field. If you think about it, QVB sine theta, right? You have a certain amount of charges, and they have a certain velocity, right? And if you multiply that velocity times a period of time, you're going to have a certain length x, right? So if you think about it, and we've got these values here, really V is just a displacement over time, right? So in other words, how far did these go? X in a period of time, and that's V, right? And so we know that Q over T, which is this portion here, the Q over T is current, so we multiply the current by the length of wire exposed, current going through and the length of wire exposed, and we can figure out the strength of the field. If you recall, N is the number of charges per unit volume, so the number of electrons per unit volume. A was the area in a wire, and then L is the length there, right? If you think about it, let's say you've got some particles in there, you have an electric field. The field is, let's say oriented like this, the magnetic field is, the electric field's like that. What's going to happen is, the electric field is going to have a force on the charge according to E equals force over Q, right? So E times Q is the force on it. So the force on the charge is QVB, and we know that as well. So we have the magnetic field force, and then we have the force due to the electric field as well. And if we have however many charges there, times the area times the length, every charge has a force on it, right? And so therefore, every single charge that you have in there is going to have a force on it according to the magnetic field that could be going through it, right? And so remember how we derived current in that unit, where we had N was the number of, was the number of charges per unit volume, A was the area, V was the velocity, and then Q is the, whatever charge. And we're using the elementary charge for these going through the wire. We could place these in here. And so what we end up getting, again, is ILB for that particular wire. And so it's important to be able to see that for this, that you'll be able to connect that idea of current, how we got current with that, and connect that to this idea here with the force on bunches of charges, right? That's what N is. It's, tons and tons and tons of charges, and over that length. And yeah, and we can get the force on that wire. So in this picture, we've got a wire that's hooked up to a cell or battery, and it's hooked up in two different ways. We have current passing through one way, current passing through the other way. And if you use the same right-hand rules, the force on these charges, or the force on the wires, makes sense based on the right-hand rule that we just looked at. And so, if you orient your hand with the one on the left, you're going to be pointing essentially into the screen. Your middle finger is going from north to south, and you'll see that your thumb is pointing down. If you orient your hand on the one on the right, you're going to be pointing basically at yourself. The current is pointing at you. Your middle finger is going from left to right, and your thumb is going to be pointing up. And so, just like we had with the first right-hand rule, with a single positive charge, now we're looking at conventional current, the flow of positive charge going through, and we can find out the force. All right, so in this one we have the current going from left to right. We have the field coming out of, or into the page rather. And I'm going to have you try this one. Go ahead and draw this on your sheet of paper and orient your hand and see if you can determine the direction of the force, and then we'll check. So go ahead and hit pause and give this a try. When you're ready to check, you can hit play to continue. Okay, so for this one, you should be pointing to your right. Your middle finger should be going towards your screen, and your thumb should be pointing towards the ceiling. And so this would be the force on this wire if there was a magnetic field, and that's the current going through. Let's try this one. Let's say the current is going into the page, and we have a magnetic field going from left to right, and we want to find the force on it. So go ahead and pause the clip and give this a try. And when you're ready to check, you can hit play to continue. All right, so you should point your pointer finger into the screen. Your middle finger should be going to your right side, and your thumb should be pointing towards the floor. And that's what would happen to this wire if it was exposed to this field.